Hello and welcome to this new series on encryption, what it is, and what its benefits are. Now this isn't going to be a big mathy series designed to get someone started in a career in cryptography. This series is for everyone, covering in general the issues that encryption solves and how you can leverage encryption to keep your files and communications secure. Part 1 is just to introduce you to the concepts of how encryption works so you can understand how to protect yourself both online and at home. First, let's introduce the cast of characters we'll be working with. Instead of just saying, person A wants to talk to person B, we'll give these people names, Alice and Bob. They want to communicate, but keep their communication secure from prying eyes. Generally, Alice is the instigator of the communication, meaning in cases where a server is involved, like a server hosting a website, it'll be Bob's server. An eavesdropper, whom we'll call Eve, is trying to spy on their communications. Eve may be just a hacker trying to get their information for nefarious reasons, and may be a man in the middle trying to spy on them. Or she may actually have the power to force Alice or Bob to give up a piece of information due to her position in, well, let's just call it the Network Snooping Association, or NSA. Now that we've got our players established, let's ask the question, why should we encrypt our data? This series will focus on 3 different aspects of privacy. 1. Privacy of communication. Alice and Bob want to talk to each other, and they don't want Eve listening in. They certainly don't want Eve to pretend to be Alice or Bob and give false messages to the other. They want to scramble their communications, which is encryption, and they want to verify that it was sent by the other person, which is authentication. 2. Privacy of storage. Let's just have Alice for this one. She has files she wants to keep secret. They may even be on a USB drive or a cloud service. What if Eve steals that drive, or hacks the cloud server, or otherwise is able to get a hold of those files? Alice doesn't want her reading the content of these files, so they need to be encrypted. Alice can also make sure that Eve hasn't tampered with important files. 3. Forward secrecy. For most of history, encryption has only been concerned with the privacy of communication at the time. In more recent decades, forward secrecy is a concern. This is keeping the communication a secret not only at the time, but in the future as well. Let's say that Alice communicates with Bob securely, and Eve can't do anything to break the encryption, but she does record the traffic. Then let's say later on, she goes to Bob as a member of the NSA and tries to get the encryption key. Forward secrecy would mean that no matter what happens, no matter what Bob gives her, Eve has no way of decrypting the recorded transmission. So there are different types of encryption, each with their own advantages and disadvantages that try to solve these problems. The first type is symmetric key encryption, also known as secret key encryption, since the key must be kept secret. Let's leave aside computers for a moment and have Alice and Bob communicate with pencil and paper. Since they both play Dungeons and Dragons, they have 30-sided dice and can generate random numbers from 1 to 30. They come up with a scheme for encoding messages as a string of digits from 1 to 30, where the first 26 are the letters of the alphabet, 27 is a space, 28 is a comma, 29 a period, and 30 a question mark. They figure that most of the communications they do can use these 30 characters. So they get together and roll the die a number of times to get lots of random numbers. Let's say they make a number of random sequences, and this first we'll call pad 1, which is these 20 random numbers. This is a secret key, a kind called a one-time pad. There are 2 restrictions with a one-time pad. It has to be at least as long as the message you're sending, and, as its name implies, it can only be used once. Now, Alice has something personal she wants to communicate with Bob, but she isn't ready to let anyone else know about it. Here's her message. Notice that there is 1 space after I, 2 after M, and 3 at the very end. Here, Alice is being clever, because this will hide from Eve the true length of her message. Now, as previously agreed with Bob, she will convert this into numbers. Note the 27s as padded spaces. You may think the repeated numbers might give Eve a clue as to what's going on, but quality encryption gives nothing away. What Alice is going to do is take her message and add the first 18 numbers of the one-time pad to each of the letter numbers. Now she needs to take any number greater than 30 and subtract 30 from it. Now Alice can send this string of numbers to Bob if she wants, plus the instruction to use pad 1, or she can go a step further and turn the numbers back into letters, in which case she gets If that looks like a random mess to you, that's because, believe it or not, it is. Assuming that the one-time pad is perfectly random, this string of letters will be perfectly random as well. It's not that the information is scrambled, the information is no longer there. This is the goal of any good form of encryption. Make it absolutely indistinguishable from random noise. Eve cannot do a thing with this string of text. Bob can because he has the one-time pad. This string is random and the one-time pad is random, but if you put the two together, you can get the original message back. Bob just takes the message and subtracts the one-time pad from the letter numbers, reversing Eve's calculation. And then he adds 30 to any number less than 1. When he converts them back to letters, he gets Alice's message intact. Notice that Bob isn't fooled by the padding. He can read the message just fine with the extra spaces. The reason why this is so secure is that even if Eve gets their scheme for converting letters to numbers, it won't do her any good. Any message 18 characters or less is equally valid as far as she can tell. For all she knows, the message might be, buy more eggs, or wanna have dinner, or even, I am not pregnant. There will be a hypothetical one-time pad that will result in each of these messages. Eve has no way of telling which one it is without the one-time pad. That's the big weakness of secret key encryption. Alice and Bob have to make sure Eve never gets her hands on the list of pads. Also, since they can never reuse a pad, once they run out, they have to figure out how to get together and securely make some more. So as good as the encryption is, it's not very feasible for these reasons. In computers, all of the numbers are binary, just strings of ones and zeros. So what Alice would do there is take the one-time pad and use a Boolean operator called XOR, or exclusive OR, and use that with the message and the pad to get the encrypted result. Bob would then take the result and XOR it with the one-time pad and get the original message back. This operator is used all over the place in encryption. So let's finish off this first video by looking at one kind of secret key encryption that is used in the real world, and we'll move on to other types of encryptions in the next video. What we're talking about here is a block cipher. In a block cipher, the message is broken down into fixed-length blocks. So since our message is 18 characters, let's break it down into 3 groups of 6. We then have a secret key that is used to scramble each block in succession. Notice that again, the message is converted into something indistinguishable from random noise. In this particular example, it works perfectly, but there's a problem with block ciphers. If any part of the message ever repeats, so will that portion of the message. So if she sends a longer message that goes, then the result of the encryption would look something like this. Notice that since the second and fourth lines are the same text being encrypted with the same key, it results in the same encrypted text. This gives Eve a clue. Anytime you see part of an encrypted message repeated, it gives the hacker a clue as to what the original message might be. This method is called Electronic Codebook, or ECB. To see a real-life demonstration, here is a graphic of Tux, the Linux penguin. Now here's a picture of Tux that's very famous among security professionals, showing it encrypted with ECB. Notice that the block cipher didn't do a very good job of hiding the picture. There's nothing wrong with the encryption key, it's just that you have areas of repeating data, such as the solid black or solid white areas. If the area is big enough, there's no avoiding it having the same output. Anytime you use the same key on the same data, you get the same result. And that's why information about the original graphic has leaked out. To fix this problem, we need to add something called entropy. Entropy in information theory refers to the amount of uncertainty in a message. If a message has maximum entropy, it is completely random. We started out with a completely random one-time pad. Here, even if we randomly generated the key, since we're using it over and over again, we need more entropy to stop these patterns from showing up. So we'll create a random number called an initialization vector, which is the same length as our block. This does not have to be kept secret, so Alice can send it to Bob right along with the encrypted message. The first block is XORed with this initialization vector, similar to what we did with the one-time pad above, and then the result of that is encrypted with a secret key. That encrypted block is then used as the initialization vector for the next block. So we only need one random string to kick things off. Each block after that gains the amount of entropy from the previous block. So if Alice were to encrypt Tux using this method, the output might look something like this. So now we have what we want. Output indistinguishable from random noise. Unlike the one-time pad, we can use the same key with a message of any length, and just generate a new random initialization vector with each message and send it along with the result. You just have to keep the original encryption key secret, which is the big flaw with symmetric key encryption. If Alice wants to talk to Bob, she has to figure out a way to get the encryption key to Bob without Eve getting a hold of it. Not only that, but she has to trust Bob enough not to give the key to Eve or anyone else. But this flaw isn't there if Alice just wants to encrypt her own private data files. She can encrypt a file with her secret key, and no one would be able to decrypt that file as long as Alice is the only one who has the key. She can put the file on a USB drive or even cloud storage and not have to worry about anyone stealing it. Since only she has the key, only she can decrypt the file. She doesn't have to rely on Bob or any other third party to help protect the key. This is known as Trust No One Security, or TNO. Now, one thing we're noticing here is that random numbers are used a lot in encryption, and that good encryption lives and dies on the ability to generate quality random numbers. We'll talk more about this later in part 1. So by now you should have a good idea of what encryption is and what its goals are. You should also have an idea of how symmetric key or secret key encryption works, and how the challenge is keeping the secret key secret. Don't worry about remembering the specifics. The concepts are all you'll need to know how to protect yourself and your data. Remember the importance of privacy of communication, privacy of storage, and forward secrecy. Remember the concept of entropy and how you should never apply the same key to the same data without introducing entropy to disguise it. We'll continue with other types of encryption in the next video.